Hello, welcome to Unit 7, Lesson 23, using the quadratic expressions in vertex form to solve problems. So last lesson we looked at the vertex form and how we can manipulate it between standard form and vertex form. So starting in vertex form and then going back to standard form. Today we're going to focus on how we can use the vertex form to help us solve problems with quadratics. Our learning objectives are: I can find the maximum or minimum of a function by writing the quadratic expression that defines it in vertex form. And when given a quadratic function in vertex form, I can explain why the vertex is a minimum or maximum. All right, let's take a look at the warm-up problem. So in this activity, we're going to be thinking back about the meaning of a maximum or minimum value of a function, which we learned back in Unit 6. We're also going to practice interpreting the language related to maximum and minimum values of functions. So let's think of some ways that you might use the word minimum or maximum. So for example, we might say there's a minimum age for voting or for getting a driver's license, or that roads and highways have maximum speeds. Could also talk about minimum wage when you're earning, when you talk about money per hour, dollars per hour. Or you could even go as far to think about the rides at Six Flags. Some rides have a maximum height, like vertical velocity, and all the rides have a minimum height. In general, we might think of minimum as the least or the least possible or the least allowable value, whereas maximum would be the greatest or the greatest possible or the greatest allowable value. So keep that in mind while you are attempting this warm-up. So here you're given the functions f and g along with their graphs. You have 4 questions that you need to complete. So go ahead, pause this video, and attempt those 4 questions. All right, let's go ahead and take a look at question 1. So question 1 says f of 1 can be expressed in words as the value of the value of f when x equals 1. Find or compute A, the value of f when x is 1, the value of f of 3, and also f of 10. So for these, all you're doing is plugging in 1 for x for each of these 3 situations. So let's start with f of 1. So that's going to be 1 minus 4 squared plus 1. 1 minus 4 is negative 3. So we have negative 3 squared plus 1. Negative 3 squared is 9. 9 plus 1 is 10. So f of 1 equals 10. Repeat it for f of 3. So this time we have 3 minus 4 squared plus 1. 3 minus 4 is negative 1. Negative 1 squared is 1, and 1 plus 1 is 2. So f of 3 equals 2. And then finally for f of 10, we do 10 minus 4 squared plus 1. 10 minus 4 is 6 squared plus 1. 6 squared is 36. 36 plus 1 is 37. Question 2 says, can you find a value of x that would make f of x less than 1, greater than 10,000? So let's look at the graph for this. So we know the blue graph is f, and we're looking for where what value of x would make it so that it's equal to less than 1. So where is y less than 1? And if we look at this graph, we can see the minimum point is right here. It never goes below the number 1. So for question 2a, no, it seems that 1 is the least value of f, and from that graph we can see it occurs at x equals 4. Occurs at x equals 4. All the other possible outputs are going to be greater than 1. And then what about where is the outputs greater than 10,000? So if we look at the graph, again, we're looking for where the output, so that's your y-axis, is going to be greater than 10,000. So yes, we can see that it will get up there to 10,000, but there's a lot of x values that could possibly produce that output greater than 10,000. So if we think about the situations, you would need to think of what x value would get you greater than 10,000. And for this example, negative 100 or 110 are both going to give you greater than 10,000. Oops. All right, let's look at question 3. So g of 9 can be expressed in words as the value of g when x is 9. So this one now wants you to find or compute the value of g when x is 9, and then find g of 13 and g of 2. So let's start with g of 9. Our equation this time is negative x minus 12 squared plus 7. So that's negative 9 minus 12 squared plus 7. Negative 9, or positive 9, sorry. 9 minus 12 is negative 3. Negative 3 squared is 9, but this negative sign will make it, negative 9. And then negative 9 plus 7 is negative 2. So g of 9 is going to be equal to negative 2. Let's do g of 13. We have negative 13 minus 12 squared plus 7. 13 minus 12 is 1. 1 squared is 1, but again, that negative sign outside of the parentheses is going to make it negative 1. And negative 1 plus 7 is 6. So g of 13 equals 6. Last, we have 2. So 2 minus 12 squared plus 7. We have our negative sign. 2 minus 12 is negative 10 squared plus 7. Negative 10 squared is 100, but it needs to be negative 100 because of that negative sign outside the parentheses. Plus 7 is going to give us negative 93. So g of 2 is equal to negative 93. So now it wants to know, can you find an x value that would make g of x greater than 7 or less than negative 10,000? So here I can see my maximum point is right here, and that is at, excuse me, that is at 712. So it doesn't ever go above 7. So no, the graph never goes above 7. Could it be less than negative 10,000? If we look here, if the graph continues out this way, there is some value. You can't really see it from the graph. But it's too hard to really see what examples because there's going to be many of them. So yes, there are going to be lots of values that produce an output of negative 10,000. All right. So just remember that a maximum value of a function is a value of a function that is greater than or equal to all the other values. It corresponds to the highest y value on the graph of the function. So for graph G, that highest y value was 7, so that was the maximum. A minimum value is the opposite of that. So we're looking at the value of a function that is less than or equal to all the other values. That one corresponds to the lowest point on the graph. So for graph F, that was 1. So the y value was 1, everything else was above that. When we're looking at quadratic functions, also keep in mind that there can only be one maximum or minimum. As you move into more complex functions such as cubic and so on, you'll see that there are more than one maximum or minimums. All right, let's take a look at the next activity. So in this activity, you're going to be identifying whether or not a vertex is a minimum or a maximum. So what you're going to do is think about the equation and how you know it's minimum and maximum. We're going to actually skip number 1, so don't worry about number 1, and just go down to number 2. So it gives you the equation along with the vertex. I want you to go ahead and try to figure out if the following functions or following vertexes represent the minimum or the maximum of the equation. So pause the video and go ahead and do that. All right, so hopefully you recalled that the way we figure out if a vertex is a minimum or maximum is if you think about whether or not the graph is opening up or opening down. So when an equation's in vertex form or standard form for that matter, if the a value is negative, then we know it opens down. So if a equals a negative value, it's going to look like that. If a is a positive value, it's going to open up. So when the graph opens down, we can see the vertex is up here, and that's a maximum, whereas when it opens up, the vertex is down here, and that's a minimum. So looking at our first equation, we see that the a value is negative, so it's going to open down, making the vertex a maximum. For the next one, we have the a value as being positive 1, so this one's going to open up, making the vertex a minimum. For h of x, a value is 4, so again it opens up, making it a minimum. K of x and m of x are both written in standard form, so for k of x, the a value is still 1, so that also opens up, making it a minimum, whereas m of x a value is negative 1, meaning it opens down, making it a maximum. So just remember that a value really does help us determine if we're going to have a minimum or maximum. You just have to think about if you are opening up or opening down. Let's go on to activity 3. All right, in this activity, it says a function a defined by p times 600 minus 75p describes the revenue collected from the sales of tickets for performance A, a musical. The graph represents a function b that models the revenue collected from the sales of tickets for performance B, a Shakespearean comedy. In both functions, p represents the price of one ticket, and both revenue and prices are measured in dollars. Without creating a graph of A, determine which performance gives the greater maximum revenue when tickets are P dollars. Explain or show your reasoning. So go ahead, pause this video, and try to answer that question. So for performance B, we can quickly identify that the vertex is right here. So that tells us when the ticket price is $3, they will make $800 in revenue. Now for function A though, which is P times 600 minus 75P, this one you're going to have to do a little work to find the vertex of. So you can think about this a couple of different ways. You could try to put this in vertex form, but to be honest, putting this in vertex form is going to require a lot of work. Instead, what I'm going to do is go ahead and find the x-intercepts. So remember, if we set it equal to 0, we can use the zero product property to tell us what the x-intercepts are. So P equals 0, 600 minus 75P equals 0. If I solve, I subtract 600 from both sides. then divide by negative 75, which is 8. So I know my two x-intercepts are 0 and 8. Now, when we think about the vertex, we talked about in the past how the vertex is directly in the middle between the two x-intercepts. So if my x-intercepts go from 0 to 8, the very middle of that is going to be 4. So this tells me my x value for my vertex is going to be 4. I still need to figure out my y value though. So to do that, I take my equation and I plug in 4 for p. So I have 4 times 600 minus 75 times 4, and I see what that equals. So when I calculate that, I see it equals 1200. So my vertex is therefore 1200. Now function b, when I looked at the vertex, I think I said 800 before, but it's actually 900. So the vertex is 3900 for function b. For function a, the vertex was 1200. I know $1,200 is greater than $900, so therefore function a, or performance a, is going to produce a higher revenue. So that's it for using the vertex to solve problems about quadratic equations. Just a few reminders when it comes to the vertex, and if we think about what our goal was, determining if it was a minimum or maximum, we can look at the coefficient of the x squared, the a value, to help us determine that. So if the a value is negative, I know the graph is going to open down, so the function has a maximum value. And vice versa, if it's negative, or positive, then it's going to be the other way around. It'll open up and have a minimum value. You could also graph the function to see if the graph has the largest y-coordinate so that the function has a maximum value, or the smallest y-coordinate so it has a minimum value. You could also find the quadratic equation, or use the quadratic equation to find the zeros. Since you know the vertex is directly in the middle of those two zeros, you could find the midpoint and then plug it into the equation to help you find the overall vertex. You could also rewrite the expression in vertex form to see what the coordinates of the vertex is. Really, we want to focus on what's most efficient. So in the previous problem we did, it talked about, we were looking at it already in factored form. It was much more efficient for me to just find that halfway point between the two x-intercepts. So that's it for today's lesson. Thanks for watching.